So again, my name is James Glosser, and I'm from Winchester, Kentucky. I recently completed the data analysis pathway, and my project is called Orbital Debris Assessment. A little bit about me. I started learning programming in 2001 with C and C++. I've worked with C Sharp since 2003. Over the years, I've also worked with Java, Python, and JavaScript. I've completed a total of four CodeU pathways. I enjoy building web and desktop applications, learning new languages and tools, and I would love to work in the video game or space industry one day. Originally, I joined CodeU because I decided to finally get into the tech industry professionally, and CodeU promotes a very welcoming and supportive atmosphere. I chose the data analysis pathway to put my analytical mindset to work on real-world data problems and also help round out my development skills. I chose this project specifically because I love everything related to space exploration, and I would love to write software or work on something that was actually used in space. Um, from the beginning of the project, I was very interested in what they call Kessler syndrome, which is a theoretical cascading scenario where the density of artificial debris in low Earth orbit becomes so high that collisions between objects cause a chain reaction, generating further debris. I wanted to be able to answer three primary questions. When did orbital growth shift from historic linear trends to more modern exponential trends, where the most orbital risk is actually concentrated, and who's contributing the most to that risk? Um, so as far as the tech stack I used, I built this project on a Python and Jupyter workflow. I used Beautiful Soup to automate data collection, then Pandas and NumPy to clean and merge the catalogs into a SQLite database, and then I finally used Matplotlib and Seaborn for the visuals. The data sets I used were the UCS satellite database and the Celestrex satellite catalog or SatCat. I also used the ESA space environment report as an external benchmark for assumptions and validation. The biggest challenge with this project was the data cleaning itself. UCS contains a lot of formatting issues, missing values, Excel artifacts, and just columns with no real analytical value, whereas the SatCat catalog is a bit more structured but lacks some of the key fields like mass, velocity, and kinetic energy, which I had to fill using a three-tiered approach. For both data sets, I focused on three key areas. Schema alignment, where I removed unused metadata and artifact columns and mapped and renamed columns so both data sets shared the same schema, which was critical for the master merge later on. Data sanitization, where I converted physics fields from strings to numeric values. This involved stripping unit artifacts like kg or km off the end of strings so I could actually perform calculations on the numbers like for math and kinetic energy or mass rather. And then categorical normalization. This was vital for my group by operations. I had to standardize different text fields. For example, collapsing five different versions of SpaceX spelling into a single canonical name. And then from there, I merged the clean data sets together to create a single kinetic master data set that underwent some final data preparation before being turned into the final SQL database. For my first primary question, my analysis identified that 2014 was the split year. Before this, the orbital population grew at a linear legacy slope of roughly 4.2 objects per year. After this, however, the growth trend shifted to a staggering 35.4% annual exponential rate. At this velocity, the population attract objects has a doubling time of just under 2 years. This means every 2 years, pretty much, we're adding as much hardware and debris to the orbital environment as we did in the entire previous history of spaceflight. For my second primary question, the data shows that collision risk is overwhelmingly concentrated in low Earth orbit. Compared to medium Earth orbit and geostationary Earth orbit, low Earth orbit contains the vast majority of high risk objects, making it the primary theater for potential orbital disasters. When you actually zoom into the LEO band, we see a massive risk density peak at about 475 km. This is a critical congested corridor where legacy debris, zombie satellites, which are just inactive or defunct satellites that can't actually maneuver, and then modern constellations all intersect. And then for my third primary question, when analyzing who actually contributes the most orbital risk, three operators stood out immediately. SpaceX, which leads the way by a large margin, followed by the Russian Ministry of Defense, and then the Japan Aerospace Exploration Agency. Together, those three operators alone account for 854 or 63.3% of all zombie payloads. Um, Building this project really helped show that I'm capable of building clean, maintainable data pipelines. Once I was able to fill, or rather clean, fill, and merge the data sets, I found that one of the most important parts, at least for me, for the process was the EDA. I explored the data as thoroughly as I could, generating approximately 40 different visualizations, and in doing so, I was able to actually find and fix most of my issues with the data pipeline. Um, if you'd like to connect, feel free to reach out, whichever way is convenient for you. Thank you for your time.
Thanks so much, James. That was awesome. It's always so cool to see the different topics that our students come up with. I think that's really interesting, and that's cool that it's such a personal interest for you. You mentioned this in your intro, but you have completed quite a few pathways with CodeU. Can you just tell us a little bit about how Python compared to those other languages, in the learning process of it, what you liked, didn't like, if anything was particularly challenging, after going through several other pathways?
Oh, yeah. So, well, learning Python compared to C# or JavaScript, at least for me, was easier. It reads a lot closer to plain English. It hides a lot of the more complicated things behind the scenes, so you can actually focus on solving problems that you're actually there to solve instead of fighting with boilerplate code or the compiler. It's It sounds weird, but I feel like I was abusing things like arrays and stuff. Like Python is really flexible in ways that some of the other languages or type strict languages isn't. So you can get a lot done with like list comprehension in a short, minute amounts of code compared to some of the other languages.
That's really cool. Well, thanks for sharing. I'm glad you enjoyed the class, and we appreciate you presenting today.
Thank you.